what we're doing here, sorry, for the people looking at the recording, the question was like an overview of graphs. And what I'm going to do is I'm going to give a very brief overview of graphs and then kind of point people to where they can go from here. So a bunch of nodes connected by a bunch of edges. And then this is like an abstract idea. You can think about it in concrete terms with just examples, right? So you can think, for example, of this graph where, you have node 0, node 1, node 2, node 3, and maybe the nodes represent airports. And then if there is a flight between airport 0 and airport 3, then there would be an edge between airport 0 and airport 3. So if the graph is weighted the way it is here, then the weight on the edge would represent, for example, the cost of going between the two airports, right? So here there is a flight between airport 0 and airport 3, and the flight costs 6. On the other hand, there isn't a flight between airport 0 and airport 2, so that's why there isn't an edge here, right? So this graph is not directed. So that means that we assume that there's just like, if 0 is connected to 3, then it's also the case that 3 is connected to 0. And the cost of going 0 to 3 and 3 to 0 is the same. You might imagine a graph where kind of in the real world, it's not always the case, for example, that flying from Toronto to Vancouver is the same cost or like really the same time because of winds and stuff as going from Vancouver to Toronto. So really probably for airports, you want a directed graph with edges that represent flights specifically, for example, from Toronto to Vancouver. So that's what a graph is, right? So are you good with this so far?
Yeah, I think most of my problem was like how to specify, how to accommodate the graphs. Like, I think there is an example in the PDF where it goes from 1 to 8, or no,
Do you want to give me the page number?
I just don't remember. I know it was in the lab.
In the lab.
I'm just wondering for the one that you have on there right now. Yeah.
Okay.
Or I guess it was for the adjacency matrix.
Okay.
I know when there is no connection in Python, you can use NumPy, set it as infinity.
Yeah.
But if we wanted to do it in C, and maybe -1 would be a valid weight, then how could we represent it?
So in C, if the weight is a double could also be infinity in the same way that the Python double and NumPy double can be infinity technically. So you can like import limits.h and it has it somewhere.
Okay.
So certainly you could, if you know that all the weights are positive, then you could use -1.
Okay, thanks.
If you don't know that all the weights are positive, then -1 might not be a good idea.
Right. Okay.
So another kind of thing that you could do is just like, so whatever, like you could do like the infinity, or you could do like the highest possible float is also a possibility, or like the highest possible double. And that's again in limits.h.
Okay, thanks.
Yeah. Yeah, sorry. So the person before, I did not quite get what you were asking about. So should I be looking in the lab somewhere?
I'm up in the lab right now. I'm just going to look for the example, but it was, I think, like, how do you, like, well, I think most of my question is related with how do you put, or if the graphs are like on order, like 1, 2, 3, or it could be like 1, 3, 5, 7,
right,
things like that.
Right. So it could be that the order really is arbitrary. A lot of the time, if the order is arbitrary and you're implementing it in Python, you could just put it in a set, and then the set itself is also unordered. If you are putting, the nodes in a list, yeah, like sometimes the order is just arbitrary.
And when we're working with the binary search for these type of questions, opening the lab, I think was like I remember doing the lab 11, I think it was.
Okay.
Yeah, we had to do the BF lists and the adjacency list base graph.
Right.
And well, I remember the TA saying something like it should be like by order depending on how they address or how they travel between nodes.
Yes.
But for
So-
example, in the example, you have like 1, 6, and 3 connected, but it was wrong to start with 6. It should start like 1, 3, and then the 6. So I'm not sure how to.
Yeah, so that's like very specific in a way that they can't address whatever the TA said. I can speak in general to graph traversal. So what is breadth first traversal? So you start with a certain node, and the order in which you want to visit the node is first you want to visit all the nodes that are directly connected to 1. So if you start with 1. So in this case, you visit 1, and then you visit the neighbors of 1. So that's 3 and 6. And then you visit the neighbors of the 3 and 6. So if you visit 3 first, then the neighbors of 3 are 2 and 4 and 5. And at this point, you're done. Right. So this is as opposed to depth first, where you want to go to one of the neighbors and then to go to a neighbor of one of the neighbors. So maybe you go 1, 6, and then to 5, and then to a neighbor of 5. So maybe you go to 4 and so on. So depth first means that when you're exploring the graph, you're trying to get as far away as possible from the original node as fast as possible, as opposed to breadth first, where you start with 1, then you want all the neighbors of 1, so 3 and 6, and then the neighbors of 3 and 6. So that's kind of what it is in concept. Does that make sense? And then now we'll talk about the implementation. But like in concept, does that make sense?
Yes.
Okay. So now in terms of the implementation, the idea is like this. You maintain a data structure of nodes that you plan to visit but haven't visited yet, right? So specifically, if we're talking about breadth first search, then what we're doing is we're saying we start with a node and then we add all of the neighbors of the node that we're visiting to a queue. So we're saying I'm visiting 1. So, okay, what are the neighbors of 1? 3 and 6. 3 and 6 are going to get added to a queue. And then what I do is every time I want to visit a node, I'm saying what node was added the longest time ago to the queue, like which one is first in the queue, basically, right? So, for example, if I go 1 and then I add 3 and 6 to the queue, so now the queue is going to be 3, 6. So I'm going to say, okay, so let me get the first node in the queue. So that's 3. So 3 is going to be visited. And now when I visit 3, I'll add all of its neighbors to the queue as well. So 2 and 4 and 5 get added to the queue. So the next time I want to visit a node, I'm going to say, which node was added first to the queue? And the answer is 6. So I'll visit 6 next. All right.
And could it be like, for example, for the first node that you want to visit first 6 and then 3, like 6, 3, and then
Yeah, so the order of the neighbors is kind of arbitrary.
okay.
So the important thing is that anytime you visit a node, you add all of its neighbors to the queue. You don't know in what order you'll get them.
Okay. Yeah, I think that was my question. I don't know if someone else has something else to ask.
For the queue that you use in breadth first traversal,
Yeah.
if you were working in C, then
Mhm.
because I know in Python you can say like pop the 0th element of your list,
Yeah.
which I don't would that just change it would just be an empty element then in your list, or would it change the
I mean, it
index?
depends how you implement it exactly, right? So it could be that, so for example, if you remember in lab 8 or something like that, we did a circular queue, right?
Right.
So that kind of provides a very natural way of being able to add to the end, but also being able to pop from the beginning, right? So you just increment the index.
And so
But
then
that's just one way of implementing it.
right.
You
So
could
then
also just say, I'll just do a list of integers data structure in C, right? So that would just keep track of, like, maybe you just do a block of memory, and then if you pop from the beginning, well, like the easiest thing you could do, I suppose, is to just copy everything one space to the left.
okay. Would it
Or
be
I think what you are going for really is a circular queue. I think that's kind of what you were thinking. Yeah.
which might be the easiest, or no, maybe
Well,
not the easiest, but
I
it could be
mean,
a good
whether
way.
it's easiest or not, I think it's kind of
Yeah.
subjective because,
Yeah.
like technically, like the problem comes when you need to expand it. There was a problem there, right? Because
Yeah.
you needed to but yeah.
Yeah. But then using a circular queue could be a good way to do it if you were working in C.
Yeah, I mean that's a legitimate way to do it. Yeah.
And what if you had your data structure as a block of memory that you allocated, then is there a way to do it where instead of having to shift everything back an element after you pop from the or remove from the beginning, if you just kind of set the address of the first
I think you're
element
reinventing
of
a
your
circular queue here.
okay. Yeah, I think. Oh, I see. Oh, okay. Yeah. And then so then when your circular queue runs out of space, then I know it's good practice for runtime to double the size of your block, but then how, like, so let's say the data starts in the middle of your original block and then wraps around and ends up back in the same place.
Yeah. So you got to rebuild the whole thing for
Oh,
this.
you would. Okay.
Yeah.
Okay. That makes sense. And for binary search trees, I remember from lecture that the worst case was when it is basically similar to a linked list,
Yeah.
which would be O of n,
That's right.
and then how it was O of log n when it was kind of like a full tree.
Yes.
So then is there a way to know, or you would just say on average it's O of log n? And
Well,
then
so okay, so here's what you can there's not so there is not so the way we did it, there is a way to know, which is that in the worst case it's O of n. It's not
right.
really O of log n on average. It's only O of log n if the binary tree is almost complete. which usually there's no reason to think it would be.
Okay.
If you build it, so like here's like an example, right? So let's say I just say like here are 32 numbers, and I want you to do an O of log n procedure for taking in an input number and checking whether it's one of those 32.
Right.
So you can then say, well, I'll make a binary tree that's complete out of those 32 numbers. I'll just figure out how. Right?
Yeah.
And then you'd say, okay, like I've already prearranged them so that they are arranged as a binary search tree. And now in this particular binary search tree, it's log 32. Right?
Okay.
Because you arranged them that way. Now, there are algorithms for which we haven't done for actually doing that automatically. It's possible to do it automatically.
Okay.
But we haven't done, no, we haven't kind of discussed how.
Right.
So yeah, so like the answer is like just a generic binary search tree. It's not actually all of log n on average. It's just like there's nothing to say there. It's just all of n in the worst case.
Okay. Okay. That makes sense. And then I know I need to go back and review, but which algorithm again were binary search trees? Or is it like, I know it's its own algorithm, but was there one of the other algorithms that we use it to do the implementation of?
Well, it's an implementation, so it's a way to implement sets and dictionaries.
Oh, okay, right.
Right, so like exactly kind of the example that I just gave.
Yeah, okay. And like when you're using a set in Python, the lookup time is O of 1 because it's not ordered like a list would be?
It's O of 1 because it's a hash table, and hash
Oh,
table
okay.
average
Okay.
are O of 1.
Right.
Specifically, like Python sets and dictionaries are hash tables.
Oh, okay.
So in Java, actually, like the usual way is to implement them with a binary search tree. In which case,
okay.
it's actually it's actually of log n, but like log n is like very, very small anyways, right? So it's
Right.
almost 1.
Okay.
But the advantage is like it's definitely O of log n, whereas dictionaries are like O of 1 on average, but O of n in the worst case.
Okay. And a dictionary would be O of n in the case of when the hash
So
table
the dictionaries are like O of n in the worst case, but they have a favorable but the average is basically O.
Oh, okay. 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 Well, thank you very much.
Sure.
Have a good afternoon.